In this video, we're going to look at transformations of graphs. We're going to start by drawing the graph of y equals x squared. We'll do this by substituting x values to work out the corresponding y values. So let's start with x equals 0. Well, 0 squared is also 0, so we have the point 0, 0. Then when x is 1, we have 1 squared, which is also 1, so we get the point 1, 1. If x is 2, we do 2 squared, which is 4, so we get the point 2, 4. And then when x is 3, 3 squared is 9, so the point 3, 9. When we substitute in the negative numbers, we actually get the same values, since negative 1 squared is also 1, negative 2 squared is also 4, and negative 3 squared is also 9. So this is the graph of y equals x squared. Now let's think about the graph of y equals x squared plus 3. So the equation of the graphs is the same, we've just added 3 to it. So when we substitute in 0, we'll do 0 squared like we did before, which is 0, but then we need to add 3. So the point is 0, 3. When we substitute in 1, we do 1 squared just like before, but then add 3, which is 4, so we get the point 1, 4. If we carry this on with x equals 2, we get the point 2, 7, and then when x is 3, we get 3, 12. And as before, when we substitute in the negative values, we get the same y values out. So the graph of y equals x squared plus 3 looks like this. Notice how the point 0, 0 moved up 3 units to the point 0, 3. And in fact, all of the points on the red graph moved up 3 units to the corresponding point on the blue graph. This means that if we have a graph and its equation, and then we add a constant number to that equation, the resulting graph will be the same shape, but it will be shifted up by a number of units equal to the number that we added. The word we use for this is a translation. In maths, a translation just means to move something. So we could say that the blue graph here is a translation of the red graph. It's been translated 3 units upwards in the y direction. It's a similar idea if you subtract a constant number from a graph as well. So let's now have a look at the graph of y equals x squared subtract 4. So this is the same graph as the red graph, apart from we've subtracted a constant number, in this case 4. If we're going to subtract a number rather than moving upwards, we move downwards. So we need to take all of the points on the red graph and move them down 4 units. So if we take 0, 0 first, that'll move down to 0, negative 4. Then if we look at 1, 1 and negative 1, 1, they'll move down here to 1, negative 3 and negative 1, negative 3. Then if we move all of the points down by 4 units, this will be the graph of y equals x squared subtract 4. We can summarize what we've learnt here using function notation. So if we have a graph y equals f of x, then the graph y equals f of x plus a, where a is that constant number, is a translation of a units up. And also, if we have the graph of y equals f of x, then y equals f of x subtract a is also a translation, but we go a units down instead. So if you add or subtract a constant number to the equation of a graph, this will move the graph upwards or downwards by that many units. But what about if we take a function and we add or subtract a number inside the function, so we alter the input rather than the output? We're now going to look at f of x plus a and f of x subtract a. Let's go back to our original graph of y equals x squared, which looked like this. If we were to write this as a function, we would say f of x equals x squared. We now want to consider the function f of x plus 2. And this is not the same as adding 2 to the function, we're adding 2 to the input of the function. So the x has changed to an x plus 2. To work out this function, we replace all of the x's with x plus 2's. So instead of x squared, we've got x plus 2 squared. So let's now draw the graph of y equals x plus 2 all squared. To do this, we're going to substitute in some points again. So let's start with x equals 0. So we need to do 0 plus 2 squared. Well, 0 plus 2 is 2, and if you square 2, you get 4. So we get the point 0, 4. When x is 1, we do 1 plus 2 all squared, 1 plus 2 is 3, and 3 squared is 9. So we get the point 1, 9. When we go to x equals 2, we have 2 plus 2 all squared, 2 plus 2 is 4, and 4 squared is 16. This one unfortunately won't fit on the graph. So let's go backwards and look at x equals negative 1. Negative 1 plus 2, well that's just 1, and 1 squared is 1. So when x is negative 1, y is positive 1. Now x equals negative 2, well negative 2 plus 2 is actually 0, and 0 squared is 0. So we get the point negative 2, 0. Then x is negative 3 plus 2 is negative 1, and the square of negative 1 is 1. So we get the point negative 3, 1. 2 more points here. When x is negative 4, we get a positive 4, so negative 4, 4. And when x is negative 5, we get a positive 9, so negative 5, 9. So the resulting graph looks like this. This time each of the points on the graph has been translated horizontally. It's gone to the left by 2 units. Most people find it initially surprising that the function moves to the left here and not to the right. We added 2 to the input of the function, and horizontally we tend to think of adding as moving to the right rather than to the left, but the function does actually move to the left by 2 units. If you give it some thought though, this does actually make sense. Each of the inputs is going to have 2 added to it before we square it. So if you take an output from the original equation, for example 9 will have come from 3 squared. So we need to reduce the input of 3 by 2 to account for that extra 2 that we're about to add. So if you input 1 and then add 2 to it, you end up with 3, which when you square is 9. So the input needs to be 2 lower than it was before to achieve the same output value, which is why the graph moves to the left. You can probably guess what happens if we subtract a value from the input of the function. So if we did x minus 3 all squared. When we added 2, the function translated 2 units to the left. If we subtract 3, it's going to translate 3 units, but this time to the right. So if we take each of these crosses and move them 3 units to the right, we end up with a graph of y equals x minus 3 all squared. You can see here that each of these points has been moved 3 units to the right. If we now return to our previous statements, we've got 2 more which we can add. So if y equals f of x, then the function y equals f of x plus a is a translation of a units to the left. If y equals f of x, then the function y equals f of x minus a is a translation of a units to the right. Now let's take a look at some exam questions on this topic. Sometimes an exam question will give you a graph, for example, here is the graph of y equals sine of x, and ask you to draw some graphs using this one. So we might be asked to sketch the graph of y equals sine of x plus 2 for x values between 0 and 360 degrees. You can think of the original graph, the red one, as y equals f of x. In which case, this graph must be y equals f of x plus 2. Since it's the same graph, we've just added 2 to the function. We know that when we add 2 to a function, we translate the graph vertically, and it goes up by 2 units. So all we need to do is mark on all of the key points of the original graph, and then move each of these points up 2 units. So the point at 0, 0 here will go up to 0, 2. The point that's at 91 will go up to 93. The one that's at 180, 0 will go up to 182. 270 negative 1 will go up to 270 positive 1, and 360, 0 becomes 362. We can now connect up these points with that nice smooth curve, and this is the graph of y equals sine of x plus 2. What about if we were asked to sketch this graph? Y equals sine of x minus 1. So if y equals sine of x is the f of x, this is f of x minus 1, since we've just subtracted 1 from that function. This means we translate the graph down by 1 unit. So if we take those key points again, and move all of those points down by 1 unit, we'll find the resulting graph. I would always recommend marking on these points and doing them one at a time, before you draw the final graph at the end. So something like this. Let's have a look at some more examples on this graph. So what if we were asked to sketch the graph of y equals sine of x plus 90? This time we're talking about changing the input of the function. The input x has been changed to x plus 90, so we have f of x plus 90. We know that when we add a number inside the function, it seems to do the opposite of what we might normally expect. So instead of moving to the right 90, we're going to move to the left 90. Let's take all of these key points and move them to the left 90. So this point here, 0, 0, will move to negative 90, 0. But I don't actually need this point because it asks me to sketch values from 0 to 360, so we can remove that one. The point at the top at 91 will move across to 0, 1. Then 180, 0 will move to 90, 0. 270, negative 1 will become 180, negative 1. And 360, 0 will become 270, 0. So we end up with this graph here. Now we haven't actually finished because we need to go all the way up to 360. So if we imagine continuing the red graph like this, then this point here would move to the left 90 degrees. So we should draw in this bit as well. And that would be the completed graph of y equals sine of x plus 90. What about if we did the graph of y equals sine of x minus 45? In this one, we've also changed the input, but we've subtracted a number. So this is f of x minus 45. When we subtract a number inside the input of the function, we're going to move the function right. So we need to go right 45 degrees. So if we now mark on all of the points of the original function, and we're going to move those right 45 degrees, 45 is half of 90, so we need to go to the right 1 square for each of these. Now you can see the final point goes beyond 360, so we don't need that one. And if we connect up these points with a nice wave shape, we end up with this graph here. So this is the graph of y equals sine of x minus 45. Sometimes you could be asked to do more than one transformation in the same question. So let's take a set of axes, and here is the function y equals f of x, which looks like this. Notice this time we haven't been given the equation of the function, we've just been told it's f of x. A question could ask us to sketch the graph of y equals f of x plus 1 and then subtract 3. This plus 1 here is inside the input, so this is going to translate the function in the horizontal direction. It does the opposite of what we expect, so when we add 1, we actually move to the left 1 unit. So this tells us to move 1 left, and this negative 3 here is outside of the function, so it means we're going to move in the y direction, and it's going to go down 3 since it's negative. So all we need to do with this function is move it 1 left and down 3. So what we want to do is mark on some of the key points from the original function, preferably ones that have integer values, so these ones here. Then once we've marked on all of these key points, we're going to move that whole function to the left 1 unit, and then down 3. So this would be the resulting function of f of x plus 1 subtract 3. So far we've learnt about 4 different transformations. You know how to translate a graph upwards, downwards, to the left, and to the right. But there are 2 more transformations that you need to know about, and we're going to look at those now. Let's consider the graph of y equals 2x minus 4. That would be a straight line that looks like this. So if we said that this was our function, f of x equals 2x minus 4, we're now going to consider the function minus f of x. If you put a minus in front of a function here, you're multiplying it by negative 1. So we need to take the original function, and then multiply this by negative 1. So negative 1 lots of 2x subtract 4. If you multiply this bracket out, you do negative 1 times 2x, which is negative 2x, and then negative 1 times negative 4, which is actually a positive 4. So the graph of negative f of x is negative 2x plus 4. Notice how this is the same as the original function, just all of the signs have changed. So instead of positive 2x, negative 2x, instead of negative 4, positive 4. Let's now draw the graph of y equals negative 2x plus 4. That graph would look like this. If you look closely at this, you can see that to get the blue graph from the red graph, we've just reflected it in the x-axis. So if we take a point on the original one, 1, negative 2, this has been reflected up to 1, positive 2. If we take another point above the axis, like 4, 4, this has been reflected in the x-axis down to 4, negative 4. This makes sense based on what we said earlier. The functions are exactly the same, apart from the signs are different. So when you input a value, you get exactly the same output value, apart from the sign has been changed. So if you ever have the function negative f of x, it's a reflection in the x-axis. And you can do this by moving all of the points that are below the x-axis the same distance above, and all of the points that are above the same distance below. Now we've just one more type of function to look at. This time the negative is not going to be applied to the whole function, but just to the input, so f of negative x. To do f of negative x, we take the original function, which was 2x minus 4, but we replace all of the x's with negative x, like this. If you expanded this out, we do 2 times negative x, which is negative 2x, and then the negative 4 remains unchanged. So if I draw on the graph for you of negative 2x subtract 4, it looks like this. This time the graph has been reflected in the y-axis rather than the x-axis. You can see this because if we take a point on the original graph, like 3, 2, this has been reflected in the y-axis across to negative 3, 2. And if we take a point to the left of the y-axis, negative 1, negative 6, this has been reflected across to positive 1, negative 6. So when we do the graph of f of negative x, we reflect the points in the y-axis. We can add these to our previous statements. So if y equals f of x, then the graph of y equals negative f of x is a reflection in the x-axis. If y equals f of x, then the graph of y equals f of negative x is a reflection in the y-axis. These are all of the transformations of graphs you need to know at GCSE level. Now let's have a look at some exam questions using these transformations. So here we have the graph y equals f of x. And we're going to be asked to draw the graph of y equals minus f of x. Since this negative here is applied to the whole function, this is a reflection in the x-axis. So we need to take each of the points on the red function and reflect them in the x-axis. I'm going to do this by starting at the left-hand side of the function over here at negative 4, 3. To reflect this in the x-axis, I need to count down how many squares it takes to get to the x-axis, and then go this many squares once more. So to get from this point to the x-axis, I go down 3 squares, so I need to go past the x-axis by 3 squares. Then for this point here, we're only 1 away from the x-axis, so I go 1 point past it, like this. Now this point here is quite interesting because it's on the x-axis. If we reflect in the x-axis, then this point won't change. This point here is 1 square below, so it'll move 1 square above. This point here is on the axis once again, so it won't change. This point here is 2 above, so it'll go 2 below. This one here is 3 above, so it'll go 3 below. This one here is almost 1 square above, so it'll go almost 1 square below. This one's on the x-axis, so it'll remain unchanged. And this point here is 1 square below, so it'll go 1 square above. There's no rule that tells you how many of these points you need to do, but I would try and do all of the points that have integer valued coordinates and also all of the ones that are on the axis. So if we join these up with a smooth curve, we end up with this graph here, and that's the answer to the question. Now let's use this graph to do a second question. So this time we're going to sketch the graph of y equals f of negative x. The negative this time is on the input of the function, so we're going to reflect in the y-axis. This is really similar to what we did before, but we reflect in the y-axis instead. So let's start with this point here, but rather than going down, we go horizontally across 4 squares until we hit the y-axis. So we must go 4 squares past this point to here. Then for this point here, we're 3 squares away from the axis, so we go 3 squares across. This point down here is 1 square away from the y-axis, so 1 square across. This point here is on the axis, so it remains unchanged. This point here is 2 squares away from the axis, so we go 2 squares across. This one is 4, so we go 4 across. And this one all the way down here is 5 squares, so we go 5 squares across. If you join all of these up with a nice smooth curve like this, you end up with this is the answer to the question. Sometimes, rather than translating the whole graph, we only need to consider what happens to one of the coordinates. Let's have a look at one of these now. So here's the graph of y equals f of x. And we're told that the point A is on this graph and it's negative 1, 3. So that's this point here. The question might say the graph of y equals f of x is transformed to the graph y equals f of x plus 1 plus 2. We're told the point A is going to be mapped to point B under this transformation, and we need to work out the coordinates of point B. So if we look at this transformation here, we've got a plus 1 on the input of the function. We know this moves it left 1 unit. This plus 2 that's been added to the function moves it up 2 units. So all we need to do is take the point A and move it 1 left and 2 up, and that'll be the point B. So we didn't need to translate the entire graph, we just did the point that we were interested in. So the coordinates of point B are negative 2, 5. Let's try a second example of this. So what if this time the function was y equals f of negative x plus 2? This time point A is mapped to point C and we need to find its coordinates. So if we look at the function we've been given, this negative x here tells us we need to do a reflection in the y-axis. This plus 2 here tells us to move the graph up 2 units. Now for this function, it doesn't matter which order we apply these in, we'll still end up in the same place. So let's start by doing the reflection in the y-axis, and then move up 2. Notice how this would be exactly the same as if we moved up 2, and then reflected in the y-axis. We end up at the same point. So this must be the coordinates of C, which are at 1, 5. Sometimes the order in which you apply the transformations does matter. So for this question here, we're going to sketch the graph of y equals negative f of x plus 3. This negative here tells us to do a reflection in the x-axis, and this plus 3 tells us to move the graph up 3. But it will make a difference which order we apply these in. If we take the original graph and reflect it in the x-axis first, we end up with this graph here. And then if we move it up 3 units, this is the final position. So we have this graph here, or if we take the original graph but move it up 3 first, and then reflect it in the y-axis, we end up with this graph here. The reason we end up with 2 different answers here is because both of these transformations apply to the y direction. If you think about it, a reflection in the x-axis is happening in the y direction, and so is moving the graph 3 upwards. So we do need to take particular care in which order we apply these. The graph that's actually correct in this scenario is the purple one, so we should have done the reflection in the x-axis first. So if you end up with a situation where you have negative f of x plus 3, you do the reflection first, and then translate. There's a second example where we also need to take care. So if we had to do the graph of f of negative x plus 3. So in this one, the negative inside the function here is going to be a reflection in the y-axis, and this plus 3 here is going to move it 3 units to the left. So if we take the graph and do the reflection first, the reflection in the y-axis looks like this, and then move it 3 units to the left, we end up here. If instead we take the graph and move it 3 units to the left first, and then reflect this in the y-axis, we end up with this graph here. So once again, you can see there are two different graphs. This time it's the green graph that's correct. So if we end up with a function like this, we do the translation first, and then we do the reflection second. So translate, then reflect. So in these situations, the order in which you apply the transformations does matter. Sometimes exam questions don't have a diagram of the graph at all. For example, graph C has equation y equals f of x. Graph C is transformed to give graph D. Graph D has the equation y equals f of x minus 4 minus 6. The point on graph C with coordinates 3, 1 is mapped to the point P. And we need to work out the coordinates of the point P. So we don't actually need the drawn graph to do this question. If we look at the resulting transformation here, we've got a negative 4 inside the input, which means 4 units to the right. And then we subtract 6 from the whole function, so this means to go down 6. So we can apply these two translations to the coordinate here. If we were to move this coordinate right 4, the x coordinate would increase by 4. So instead of being 3, it will go up to 7. If we move it down 6, the y coordinate will go down 6. So we do 1, subtract 6, which is negative 5. Let's try a second example like this. So this time we're going to have a different transformation, f of negative x plus 1. And we have the point 5, 9, which is going to be mapped to the point P. And we need to work out the coordinates of P again. So this time we have f of negative x, which is a reflection in the y-axis, and then plus 1, which is moving up 1. So we can just apply both of these to the coordinate 5, 9. If we're going to reflect in the y-axis, the y-coordinate remains unchanged, but the x-coordinate will take the opposite sign. So when the x-coordinate was originally 5, it will now become negative 5. Then we've got to do this translation, so we need to move up 1, which will mean the y-coordinate will increase by 1 from 9 to 10. Sometimes in exam questions, we don't need to deal with a graph or coordinates, we're just dealing with the function itself. So let's take a look at this one. Graph P has the equation y equals x squared minus 5. Graph P is reflected in the x-axis to give graph Q. We need to find the equation of graph Q. So in this one, graph P is reflected in the x-axis. We know this is the transformation y equals negative f of x. If you think of the original function as being y equals f of x, then we've got f of x equals x squared minus 5. If we're going to do negative f of x, we just take the original function, but apply a negative to it. So we have y equals negative x squared minus 5. If you expand out this bracket, you get y equals negative x squared, but then negative 1 times negative 5 is positive 5. So the equation of graph Q is negative x squared plus 5. Let's try another example like this. So graph P has the equation y equals x cubed plus 2x plus 1. Graph P is translated 3 units to the left to give graph Q. And we need to find the equation of graph Q. And we've been asked to give it in a particular form, y equals x cubed plus ax squared plus bx plus c. So this time the transformation is a translation 3 units to the left. We know this is f of x plus 3 since it does the opposite of what you might expect. To do f of x plus 3, we're going to take this original function up here, but replace all of the x's with x plus 3's. So we end up with y equals, instead of x cubed, x plus 3 cubed, instead of 2x, 2 lots of x plus 3, and a plus 1 at the end. So we need to expand out all of this because they've asked for it in this particular form. When we expand out x plus 3 all cubed, this is x plus 3 times x plus 3 times x plus 3. So we have a triple bracket to expand here. I'm not going to go into detail about how you expand this triple bracket, that's a whole nother video. I'll put a link to that one in this video's description. But the result from the expansion would be y equals x cubed plus 9x squared plus 27x plus 27. We can expand this bracket here quite easily though. 2 times x is 2x, and 2 times 3 is 6. And of course we've got this plus 1 at the end. Now all we need to do is simplify. We've got y equals x cubed plus 9x squared. Then we can collect together these like terms here. 27x plus 2x is 29x. And then also the constant terms here. 27 plus 6 plus 1 is 34. And that's your answer to the question. You can see it now matches the form they asked for, x cubed plus ax squared plus bx plus c. Thank you for watching this video, I hope you found it useful. Check out the one I think you should watch next, and subscribe so you don't miss out on future videos. And check out the exam question booklets on this topic that I've put in this video's description.